Hi guys. So today is going to be mostly review from Algebra 1. Just about everything that you're going to see today is something that you probably saw in Algebra 1, so hopefully this will be a pretty easy review for you guys. But even if it's a simple review, it's a really important review. We're going to spend a lot of time in the next few weeks on quadratics. And if you can't really remember some of that foundational stuff that you guys did in Algebra 1, it's really important that you relearn it now. So the first thing we're going to start with is graphs of quadratics. And the way we're going to do this is the same thing we did with absolute value. We're going to look at the parent function, and we're going to look at transformations. And then we'll look at a few other forms, but the most important thing to understand is the parent function and the transformations. So the quadratic parent function, as you may remember, is y equals x squared. So let's go ahead and sketch the graph to see what it looks like. Easiest way to do that, plug in some points. If I plug in 0, 0 squared is 0. If I plug in 1, 1 squared is 1. If I plug in 2, 2 squared is 4. If I plug in 3, 3 squared is 9. Now let's do some negatives. If I do -1, -1 squared is a positive 1. -2 squared is a positive 4. -3 squared is a positive 9, which leads us to our parabola shape. And 9 is going to go off my graph, but you guys get the idea. So that is my quadratic parent function. Now let's talk about those characteristics. So really just to kind of review those things. Domain for this is negative infinity to infinity. There is nothing that stops it on those x values. Every x value is possible. Range, we always list bottom to top. The lowest y value here is 0. It does touch that, so it gets a bracket and continues to infinity. This graph is increasing, so as my x's get bigger, the y's are getting bigger on this section of my graph. So that is from 0 to infinity. It's decreasing on this section of the graph, so from negative infinity to 0. Positive is when this graph is above the y-axis, which is just about everywhere. The only point it's not is when it's 0, because your graph's not really positive at that point. So this graph is positive from negative infinity to 0, and then again from 0 to infinity. We have parentheses on the 0 because when x is 0, the y value is 0. It's not a positive number. This graph does not have any negative y values. And then our parabolas are going to have an axis of symmetry. So if you remember, that's kind of the dotted line that we can draw. It goes through the vertex, and that's basically where we could flip that graph over and it'd be the same on both sides. So in this case, that axis of symmetry is x equals 0. Because that axis of symmetry is x equals 0, well, then that tells us that this graph actually has symmetry, which means this graph has y-axis symmetry. So this is an even function. And if you remember from the first unit, that means that f of negative x is equal to f of x. Now, not every quadratic will hold that property true, but any quadratic that has that symmetry on the x-axis, on the y-axis is going to have that property be true. So anywhere that your axis of symmetry is the line x equals 0. All right, extreme of this has a global minimum. It's also a relative minimum, but more specifically, it's a global minimum at 0, 0. And that point is the vertex. Your vertex is always going to be either a global minimum or a global maximum on these parabolas. And then finally, end behavior. As x approaches negative infinity, f of x is approaching infinity. And as x approaches positive infinity, f of x is approaching positive infinity. So just to review some of those characteristics from the first unit, those are going to continue to come back in the units to come, so don't forget them. Something else we talked about in the first unit were transformations. Now, you guys are probably going to get really sick of seeing this chart because you're going to see it with just about every single parent function we do this year. So, if you remember, all of these over here on the left, those transformations are all horizontal. They deal with the x, what's inside the parentheses. So, what we're going to do is we're just kind of a refresher on what that actually means. All right, f of x minus h is a shift right. F of x plus h is a shift left. B times x, it depends on the value of b. If b is greater than 1, then that is a horizontal compression. If b is in between 0 and 1, it is a horizontal stretch. And then if you have a negative inside the parentheses like that, that is a reflection over the y-axis. So what we're going to do now is show what does that actually look like on a quadratic equation. Well, think about the parent function, f of x equals x squared. If I do f of x minus h in this function, that means I replace x with x minus h. So what that would look like is f of x equals x minus h in parentheses squared. So that is what a shift to the right is going to look like for us. All right, f of x plus h. Again, if I were to replace x, it would be x plus h in the parentheses squared. So again, anything in the parentheses is going to be a change horizontally. Horizontal stretches and compressions will also be inside the parentheses. Now be careful about that. You may be tempted if you see something like this. Just note that 2 is not being squared. So that 2 is not a horizontal stretch or compression. If it was, you specifically would see those parentheses right there in order for that 2 to actually be squared to be a horizontal stretch or compression. And then finally, f of negative, I keep forgetting to write f of x. Man, f of x equals negative x squared. Now one thing you'll probably notice, well, negative x squared, that's the same thing as x squared. But again, think about what that means for your question. If you reflect that parabola over the y-axis, it has that y-axis symmetry. It's an even function, so it's going to be the same thing. So what that means for us is basically this transformation is really not going to affect the way our graph looks. If you see it, you do need to be careful because it can affect your vertex, but it's really not going to change our graph in too many ways. All right, then vertical changes. F of x plus k is a shift up, minus k is a shift down. If a is greater than 0, that's a vertical stretch. And vertical compression. And a reflection over the x-axis. Again, what this will look like, this will be away from that x squared, outside of any parentheses. So if I have x squared plus k, okay, because I'm adding that to, remember, f of x is x squared. That's my parent function. If I add k, I just add k. It does not change what's being squared. All right, x squared minus k. A times x squared. And again, that would look like something like we just did. 3x squared. That would be a vertical stretch. And then if I have a negative, again, not in the parentheses, the negative is not being squared in this case. So even if I have both the stretch and the reflection, okay, it will not be in the parentheses. If it's in the parentheses, that's when it would be horizontal. All right, so when it comes to multiple transformations, kind of the format we want to see with multiple transformations is something like this. That's because that makes it really easy for us to be able to identify our vertex. So what you'll notice is that b value is not next to the x, it's been factored out. And the reason for that is, again, it makes it very clear then what our vertex is. So for example, if I were to have something like this, right now it's kind of hard to tell what my vertex is. So what I would need to do is factor out that value, and it's still being squared, but by factoring it out, it makes it clear that's my horizontal compression, and now the x-coordinate of my vertex is 2. So it makes it a little bit easier just to see what your vertex is. Now, you're not going to see a lot of quadratics that are in this form, but we will see this form come up in multiple parent functions going forward, so it's really important to get kind of used to just that process of factoring out that value. Now, notice, whenever we factor it out, let me give you another example. All right, when I factor that out, it does not come out of the squared portion. And I don't know why I made that 3. Let me make that a different number. Okay. So I can rewrite this. The 3 can get factored out. But notice the 3 is still within the parentheses of what's being squared. Now with absolute value, we had that really unique property. We could take that 3 and we can move it out. You cannot do that for quadratics because the number that's out there is not 3. The number that's there actually is 9 because 3 is being squared. Now, if you want to move a 9 out, you can. But again, don't just factor that value all the way out and make it your vertical stretch, because it's not. It's going to be a different value because it's being squared. So like I said, we're not going to see those horizontal transformations too often with quadratics. That's going to come up a lot more in future units. But right now, we're going to look at some basic examples. Hopefully, this is pretty similar to what you guys saw in Algebra 1. But if it's not, it'll be good review. All right, this is going to be pretty similar to what we did with absolute value. The only difference is it's a different function that we're actually graphing. Okay, so just like we did with absolute value, the first thing we're going to do is we're going to identify what are the transformations from the parent function x squared. And I should use a pen, not a highlighter. Well, on this first one, that negative on the outside, that's a reflection over the x-axis. The 1/2, that is a vertical compression. The -1 is a shift right, and the +3 is a shift up. So the next thing we're going to do is we're going to figure out what our vertex is. Okay, our vertex in this form is very easy to identify. Okay, it's x minus h. H is the x-coordinate of the vertex. So my x-coordinate of my vertex is 1. And then plus k, well then the y-coordinate of the vertex is 3. So my vertex here is 1, 3. Now when it comes to graphing, the first thing I'm going to do is I'm going to graph the vertex. So I'm going to graph 1, 3. Then what we're going to do is we're going to see how this graph has changed from the parent function. So what I like to do, there's a lot of different methods for graphing. If you want to just plug in points, you're welcome to plug in points. In order to have an accurate graph, you need to have the vertex and you need to have at least 2 other points. So if you want to just pick points to plug in, go ahead. Just be careful that you pick points that are easy to graph. Don't pick weird, crazy decimals that are hard to see. So the way I'm going to graph this is the same process that I'm going to use for all of our parent functions going forward. I think it makes the process, I think, a little bit faster. And I also think it helps us out when we go the opposite way and we see a graph and we try to write the equation. So what I'm going to do is I'm going to list the pattern of the parent function. So the pattern of the parent function, from the vertex, I went right 1 and up 1. Then I went right 2 and up 4. Then I went right 3 and up 9. And that's how I moved from the parent function's vertex. Well, what's different now between this graph and the parent function, first of all, is the vertex. So this is not going to be how I'm moving from 0, 0. This is going to be how I move from 1, 3, because that's my new vertex. So from the point 1, 3, this is how I'm going to move. Now, these are not coordinates. This is just how I'm moving from that vertex point. Now, the other thing I have to consider, this graph is not going to have the same shape as my parent function. We already took care of this transformation and this transformation by moving the vertex. What we also need to consider, though, is that this graph has been reflected and compressed. So we need to see how is that going to change the pattern that we're moving from. Well, what it's going to do is it's going to compress it vertically and reflect it. So it's going to change that up and down number. So instead of going right 1 and up 1, I'm going to go right 1 and down 1/2. I'm going to go right 2 and down 2, right 3 down 9 over 2, which is 4 1/2. If I want to add another point to make it a little easier to see, I can go ahead and follow that pattern, 4, 16, and that would become down 8. And again, these are not coordinates. I'm doing this a little different. This is how I'm moving in relation to the vertex. This is taking these transformations into effect. Now, the reason we don't need to worry about this with our vertex is because think about where the vertex originally was. The vertex was originally at 0, 0. If you multiply 0, 0 by negative 1/2, it's still 0, 0. So the only thing that affects it is that shift right and shift up. And then since this is how we're moving in relation to the vertex, it's already considering the shift when we do it. So let's go ahead and plot those new points. So from the vertex, I'm going to go right 1 and down 1/2. From the vertex, I'm going to go right 2 and down 2. From the vertex, I'm going to go right 3 and down 4 1/2. And from the vertex, I'm going to go right 4 and down 8. Now we also know this graph, because it's a parabola, has symmetry. So I'm going to plot those exact same y values symmetrical on the other side of that vertex, because this has an axis of symmetry at x equals 1. And now I have a pretty accurate graph. It's a little bit easier to get than just plugging in values. Now again, if you want, yes, you can go ahead and say, hey, if I plug in 4, what do I get? I just say be careful with that, because it's really easy to make some of those mental math mistakes if you're trying to do it quickly. And again, I do like this process because we're going to use it throughout the year to do our graphs. And I think it's going to make it easier when we go backwards and we try to write the equation. That's kind of one of the things I like about it. All right, so now that we have our graph, let's go ahead and list the characteristics. Domain, negative infinity to infinity. Range, bottom to top, negative infinity to 3. It touches 3, so it gets a bracket. Increasing and decreasing. This graph is increasing on this section. So from negative infinity to 1, decreasing from 1 to infinity. All right, so let's try another. Again, first thing we do is we're going to list the transformations. This graph has a vertical stretch, and it's shifted left 3. That means that the vertex is going to be at negative 3, 0. So it's the opposite sign of this, and then whatever our vertical shift is, which in this case there's none. So I'm going to plot that first. Axis of symmetry is going to be that x equals negative 3. It goes through the vertex. And then let's plot the points coming from this point. So from negative 3, 0, we're going to follow that parent function pattern. Well, our parent function goes right 1, up 1, right 2, up 4, right 3, up 9. How this has changed, though, is that it's been stretched vertically. So that's going to change how much we're going up. So instead of going up 1, we're going to go up 2. Right 2, up 8, and right 3, up 18. So from that vertex, right 1, up 2. Right 2, up 8. Right 3, up 18 is going to be way off my graph, but that just gives you some more points if you need them. And then we're going to reflect those same points on the other side of that vertex because it has that symmetry. So again, once you get used to this, I do think it's a lot faster to actually be able to draw graphs this way. Domain, this is going to be true for all quadratics. Range has a bracket to infinity. End behavior. My son is talking to you guys. He likes math. As x approaches negative infinity, f of x approaches positive infinity. As x approaches infinity, f of x approaches infinity. And then positive, negative intervals. Well, this graph is almost entirely positive like our parent function. The only place it's not is that one spot right there. So my positive intervals, negative infinity to negative 3, union, negative 3 to infinity. And then this graph does not have any negative intervals. All right, so now what we're going to look at are some more graphs, but we're going to look at these in a couple different forms. So there's really 3 forms of a quadratic that we're going to focus on today for a quadratic. You've probably seen these all in Algebra 1. The one we just looked at is vertex form, where you have a x minus h squared plus k. And that's the easiest one to notice transformations on. Now there's 2 other forms of a quadratic that we're going to see. So one of these other forms is standard form. Standard form is probably the one you saw most often when you were solving quadratics. So standard form is ax squared plus bx plus c. And then you also have root or factored form, which you also probably used for solving. And this is a x minus, we'll say r1, and x minus r2, where r1 and r2 are the roots, the zeros, the x-intercepts. And a standard and root form, you'll see those most often when we're solving, but we also want to be able to graph those forms. All right, and then as we talked about the parts of a quadratic, 2 things that we're always going to see, the axis of symmetry. We can find that on vertex form pretty easily. It's just x equals h. But on non-vertex form, and if it's in standard form, it may be easier to do that a different way. So we can do x equals negative b over 2a to find the axis of symmetry in standard form. We also, for root and factored form, one thing we know about the axis of symmetry is that it's halfway in between those roots. All right, vertex is going to be the x-coordinate of the axis of symmetry. So it's either going to be hk, or if it's in standard form, we can do negative b over 2a, and then f of negative b over 2a. And that's the other way that you can find your vertex if it's standard form. So what we're going to do now is we're actually going to graph these in standard form and root form. I went too far. All right, so other thing that you can do, if you remember completing the square, you can actually use completing the square to rewrite this in vertex form. And that's what we're going to do next class, but we're going to save completing the square for a separate day because it's probably been a while since you guys have done that. So if we don't use completing the square, to find the vertex, we can use what we just talked about, where it's x equals negative b over 2a. So that's going to be the x-coordinate of my vertex and my axis of symmetry. So negative 4 over 2 times negative 2, which is negative 4. So the x-coordinate of my vertex is 1, my axis of symmetry is 1. To get the y-coordinate, take that 1, plug it in. So that's going to be 7 minus 2, which is 5. So I'll go ahead and plot my vertex just like I've been doing, so 1, 5. And now, just like we did, this is again another reason why I prefer that other method, we can still follow that parent function pattern without having to go through and plug in all these other values and find more y coordinates. So what I know, that -2, that's how my graph, we know it's been reflected, and that's also the stretch that I have. That's that a value, so just like we had on the original. So again, from the vertex, so from 1, 5, how I'm going to move, okay, that's how I'm moving from there. That value has been reflected and stretched by 2. So from the vertex, I'm going to go right 1, down 2. Right 2, down 8. Right 3, down 18 is not going to fit on my graph. And then again, same thing on the other side. All right, domain. Hopefully you see a pattern now. Range. Increasing from -infinity until 1, decreasing from 1 to infinity. All right, this next one is in root form. Okay, so root form tells us where the roots are, okay? Factored form. This value out in front, that's your stretch or compression or reflection. So no matter what this number is, it does not affect the fact that the opposite of those are going to be my roots. So my roots are going to be -3. You're such a happy boy. So I'm going to go ahead and plot those roots on my graph. So -3 and 5 are my roots. Well, I know that the vertex is going to be halfway in between those roots. So halfway in between those is 1. That means that my vertex is going to have an x-coordinate of 1. And my axis of symmetry is x equals 1. So to get the y-coordinate, again, I can just take 1 and plug it in. So that means I have 1/2 times 4 times -4. So 1/2 times -16 is a -8. And that's enough points for me to have my graph. Domain, -infinity to infinity. Range, -8 to infinity. And behavior, as x approaches -infinity, f of x is approaching infinity. Missed my arrow there. And as x approaches positive infinity, f of x is approaching positive infinity. So those are the different forms of a quadratic. We are going to come back to these, especially when we start writing equations, and you'll see some of these forms when we solve. But really just want you guys to see the different forms of graphing. Now, the other thing we're going to look at is a little bit of solving review. We're going to do a lot more solving next class. But we're going to look at the two probably most common solving methods you did in Algebra 1. The first one is factoring, and this is the most important one. And you're going to hear me say this a lot next class. Factoring is so important. It is probably the most important thing you need to get out of this year. So you saw it in Algebra 1. We're going to do a lot more this year, and we're going to look at some kind of harder ones this year. But this skill is an absolute must for your future math classes. And I don't mean just that you kind of understand it. I mean, you got to know this like you know your multiplication facts. Factoring needs to be quick, simple, and easy for you guys. And that is incredibly important. Now, again, we'll spend some more time next class on this, and we'll see it throughout the year. But if you do not remember factoring from Algebra 1, you may want to get some extra reviewing because this is so important. So important. You do not want to solve every quadratic by quadratic formula. It will take way too long. It will be really annoying, and it's really easy to make mistakes. Factoring also is going to be necessary for other processes we do later this year. Okay, so let's go ahead and actually solve. So one thing you hopefully remember about factoring is you have to, or solving quadratics in general, the first thing you need to do is set it equal to 0. Then, if a is 1, okay, if this value is 1, these are really easy to factor. All you do is you look for numbers that multiply to -6 and add to -5. Well, in this case, those numbers are -6 and 1. So x minus 6 and x plus 1. So my solutions then would be x equals 6 and x equals -1. Way faster than quadratic formula. All right, look at the next one. When a is not 1, Now you've got really two options on how you factor this, the long way and the slightly faster way if you're good at mental math. I'm going to start with the longer way, which is the normal way that you probably have done this. There's nothing wrong with doing it this way. You start by multiplying A times C. You're looking for numbers that multiply to that and add to this middle number. So what multiplies to 12 and adds to negative 7? Well, those numbers are negative 3 and 4. So what I'm going to do is I'm going to rewrite this problem. I'm not going to change it in any way. I'm just going to rewrite it. And I'm going to rewrite the middle term into those two new numbers. So minus 3x minus 4x plus 6. This has not changed this equation in any way. I've just simply rewritten this into this. Now what I do is I use grouping. So I look at these first two terms and I figure out what's common, x. If x gets factored out of those two terms, I'm left with 2x minus 3. Then I look at the next two. Whatever sign is here, I keep. And then I take out what's common, which in this case is 2. So what you'll probably notice is that those parentheses are the same. Well, that tells us that, so since those are the same, then what we do, that's our first factor. Everything that's not in the parentheses is our second factor. To get our answers, basically you're setting each factor equal to 0. So x equals 3 over 2, and x equals 2 are our two answers. Now, the other way that you can factor this, and this is something we'll talk about a little bit more next class, if you're really good with mental math, this may be faster. So what we're going to do is kind of guess and check to try to get to this step without having to go through these two steps. So I'm going to go ahead and erase that work. And I'm going to basically just start with my parentheses. So what we're doing is basically, every time we factor, we're reverse foiling, okay? We're coming up with what this would be. If I were to take the factored form and multiply it out, I would get the original. So we're kind of just working backwards. Well, what I want, whenever you FOIL, you do your first, your outer, your inside, and your last. So what we're going to do is we are going to figure out what has to go in those blanks to create what we have. Well, if we start with the first numbers, okay, our first numbers are going to multiply to be 2x squared. So in this case, this one's pretty easy because the only things that multiply to be 2x squared are going to be x and 2x. Okay? The last two numbers are going to multiply to be positive 6. So we have a couple options there, 1 and 6 or 2 and 3. So again, this is kind of where the guess and check part comes in. So let's say I do 3 and 1. Okay, that's not going to work. We already know what our answer is. Oh, I don't know why I did 1. 3 and 2. Okay, so if I do a 3 there and a 2 there, okay, yes, that is going to multiply to give me 6. But what I need to check are these middles. Okay, let's say I make them both plus. So if I check those middles, 3 times 2 is 6x, plus 2 times x is 2x. 6x plus 2x does not give us 7x. So I need to figure out what values basically here are going to add up to be that negative 7x. Well, first of all, it's negative. So these are going to need to both be minus. And then I can kind of guess and check with those values that multiply to 6 in order to get that. So again, this is what we know our answer is. When I check those middles, that becomes negative 4x minus 3x, which is a negative 7x. Again, we'll look at that a little bit more next class, but for those of you guys who are pretty good with mental math, it may be a faster way to factor than going through that whole process. There's nothing wrong with going through that process, though. It does work every single time, so. All right, a little bit more factoring. So again, first thing I need to do here is set this equal to 0. A really common mistake is that people will just divide both sides by x. You can't divide by x because you'll lose part of your solution. This is quadratic. We need to set this equal to 0. Do not divide by x. You'll lose part of your solution. So now, factoring, remember part of factoring is just GCF. X comes out, x minus 3 is left, so my two solutions are x equals 0 and x equals 3. If you just divided by x, okay, you'd be losing part of that solution. And then the last one. So this was a form of factoring that, again, we'll look at a little bit more tomorrow. This is called a difference of squares. There are two terms. There's a minus in the middle, and you know the square root of both terms. If that's the case, the way it factors out, you take the square root of both terms. One factor is plus, the other factor is minus. A difference of squares is one of the easiest things to factor, but sometimes it can be hard to recognize, so make sure you're looking for it. So two terms, minus in the middle, and you know the square root of both terms. One of them is plus and one of them is minus. Now our solutions then would be negative 5 over 2 and 5 over 2. All right, so the last thing we'll look at, again, this is the one most of you guys probably remember, quadratic formula. Yes, it works every time. However, it is not the best option a lot of the time. It is a lot of times the slowest option and one of the easier options to make mistakes on. Please do not only rely on the quadratic formula to solve quadratics. If you can factor, factor. We'll look at completing the square. Sometimes that option may be better. Quadratic formula is kind of the one you just fall back on if the other ones don't work because it's slower. If you don't remember quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And the way you probably should have learned it if you didn't is you sing Pop Goes the Weasel. So it's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's the way I've always learned it. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So I get 2 plus or minus the square root of 4 plus 8, which is 12. And now we need to simplify it. And this is where the mistakes tend to happen. So be careful. First of all, do not simplify that 2 and that 4 yet. You cannot do that yet. In order to simplify, there has to be something here that is divisible by the same thing you're dividing this number by. So you cannot just simplify those numbers. Do not do that. That's probably the biggest mistake that I see. So the first thing we're going to do is we're going to simplify the square root of 12. And now that both of these numbers are divisible by 2 as well as the 4, we can divide all of those by 2. The second most common mistake I see is if you divide this by its number, some of you guys just make it disappear. It doesn't disappear, it becomes 1. So this becomes 1 plus or minus root 3 over 2. All right, same idea on the next one, but again, first thing we need to do is set it equal to 0. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So this becomes 4 plus 20 is 24. And again, we cannot simplify those 2's yet. You have to simplify the square root of 24 first. So the square root of 24 simplifies. We could take out that 4, so that becomes 2 root 6. And again, when we divide those 2's, this does not disappear. It becomes a 1. So this becomes 1 plus or minus the square root of 6. All right, so that is your big, long quadratics review. Again, we'll spend some more time with solving and factoring over the next few days. Your quiz that you'll have, the first one, is going to have a lot of factoring on there. So just be prepared and be ready to factor. Next class is going to have a lot of factoring and a little bit more quadratic solving. So that is it.